So thank you for being well in time. So the switch over is now to the session experimental controls, which is meant to be co-chaired by myself. My name is Roland Müller. I'm working for the Helmut Center Berlin, and my co-chair is Dan Flatt from Stanford. He unfortunately didn't make it so far from the California to this virtual room, but I think he will be there in a minute. Oh, he's there. So sorry, I admit. So it's my pleasure to. It's an ultra condensed program. So I ask everybody to cooperate with us to stay in time, because the previous session was very well in time. We have a bit of time reserved because the parallel session has a lag of nearly 7 minutes, so we can relax to get in the final stretch to the finishing session together with the parallel session. So it is meant that the introduction of the first speaker is done by Dan. So please, can you take it over? Dan? No, it's not here. So it's the first speaker is Laura Munoz from the Synchrotron Soleil. She is working at a robotics engineer and helping to improve the robotics support within the Synchrotron light source Soleil. So I'm happy to have her presenting what she's doing with the robots. Laura, can you share your screen?
Yes. Okay. Can you hear me?
Yeah, perfect. Thank you.
Yes, it's okay. Okay.
All fine.
Okay. Okay, so hello everyone. My name is Laura Munoz, and today I'm going to talk about 2 robot applications that have been developed in Soleil using robot manipulators. I'll begin by an introduction, then I will describe the 2 applications that have been developed to carry out power diffraction measurements and to characterize the magnetic field of the insertion device magnets. To finish, I will give you the conclusions and the future work. So an industrial robot, it's an automatically controlled, reprogrammable, multi-purpose manipulator, programmable in 3 or more axes. There are 5 types of industrial robots, but the most common one is the articulated robot. An articulated robot has at least 3 rotary joints and closely resemble to the human arm. This type of robot is used in many process automations, including welding, painting, assembly, as well as machine to tending and pick and place. In asynchrotron, the industrial robots are basically used to do repetitive tasks over long periods of time. Thus, the robotic sample changer is one of the most deployed applications, which correspond to a pick and place. In this kind of application, the robot picks samples from some sample store and places them on a diffractometer. We can find automatic sample changers in beam lines to perform, for example, X-ray diffraction or macromolecular crystallography. The other most employed application uses the robot as a detector holder. Here, the robot will position the detector in its 3D workspace to accomplish some experiments, as for example, Bragg CDI. But the use of robots is not limited to these two applications. So there are also other applications, such as positioning samples. Soleil, some years ago, came up with the idea to further automate beamlines, and it was concluded that the manipulators would be a good solution. Then a robotic standard was developed with the purpose of integrate robots into existing processes and to make evolutions more easily. The standard consisted of setting a brand for the mechanical arm and for the controller, and so we choose Stobly. And also a software interface was set in a form of a C++ library to facilitate the communication between the robot controller and Tango. From the control system point of view, the robot controller has methods. Methods are routines used to communicate and to act on the physical environment. Some methods can be applied to any robot environment, so they are generic. And we have, for example, ordering the robot to switch on actuators or moving the robot to a parking position. Some other methods are specific to an application. This is mean that they are task specific. Like example, we have picking up a sample or positioning a detector in the 3D space. So, the two applications that I will talk in a minute use the Stobly TX260L robot, since the low capacity, the radius of action, as well as the positioning repeatability were enough to cover the application requirements. The first application to emerge from standardization is an automatic sample changer for powder diffraction measurements installed in the Crystal beamline. Crystal is a beamline dedicated to study single crystals and powders. In the figure, you can see the experimental platform, which has a two-circle diffractometer, which also has two detectors to carry out experiments. The platform also has the sample store with a capacity of 36 samples, and the robot is mounted on a mobile chassis, which has the controller, the inputs, outputs modules, and the fluid panel. The robot is mounted in this mobile chassis in a way that it can be moved in case of non-use. So in the following video, we're going to watch how the application works. So it begins with the automatic mounting of the sample, where the robot takes the sample to be analyzed, checks if there is any other sample on the diffractometer with the help of a laser sensor, and if there is not any sample, it will place the sample on the diffractometer. Then the task of the self-centering of the sample will begin and this is done using image processing. Then, when it is finished, the scanner with the detector continues. So finally, the robot takes the sample from the diffractometer and put it back to its place on the sample store. But we will not see this stage of the process on the video. So the second application aims to accomplish the magnetic characterization of the hundreds of modules or magnets that compose an undulator. For this application, the robot is mounted on a pedestal, unlike the Crystal application where it was on the mobile chassis. Here in the photo, we can see the boxes where the magnets are stored vertically, as well as the robot tool. This tool has a 2-finger gripper and a force torque sensor that it is used to position the magnet on the test bench correctly. So here, the robot takes the magnet to be analyzed. It places it on a plate. So after, it can be correctly placed on the test bench. Then the Hall effect proof that cannot be observed on the video, but it's in there, and a rotating coil, it's here, will carry out the magnetic measurements. So once the measurements are finished, the robot turns the magnet over and places it on the bench to do magnetic measurements of the other side of the magnet. And finally, the robot takes the magnet from the bench and puts it back to its position in the box. So in the top figure, as you can see, the final position of the module on the test bench. So it's in the execution of this task where the torque force sensor is used. So regarding the software, we have a robot device which uses the generic and the specific methods to communicate with the robot controller. The whole process is managed using a high-level scripts, taking the advantage of the Tango bindings. So this approach allows to easily integrate the robot into the architecture defined by the different streamlines or teams. So in the case of the crystal application, we used Python, and for the magnetic characterization, Igor Pro was used, but we can use any other binding if necessary. So in conclusion, the standard allows to easily integrate robots in existing processes. 2 robotic applications have been deployed using the standard, and these applications have allow us to carry out the measurements 24 hours a day. Once one of the application was fully developed and designed by the Soleil teams, and the other one was developed by a subcontractor. In perspective, 10 other applications have already been identified to automate some experiments, which lead us to face new challenges as collision avoidance, manage more complex environments, and we also must cover high demands on accuracy and stability. So I finished. Thank you very much for your attention.
Thank you, Laura.
I don't know if you have any question.
Do we see any, are there any questions in the Q&A? All right, then, thank you.
Okay.
Yeah, thank you very much. So let's proceed to our next speaker will be Nathan Cook from Radiosoft. Nathan is a senior scientist there, and his expertise is widespread. So to condense it to what I find interesting is he is doing fast things or tiny things in his computational physics, covering plasma accelerator applications and wavefront analysis for the analysis of beamlines. And I'm looking very much forward to his presentation. So I don't want to spend too much time. Please introduce yourself better. Nathan, take the floor. Thank you for being here. Can you share
Thank you very much for the nice introduction, Roland. Can everyone see my screen?
Yeah.
Okay.
It's a bit wide and therefore a bit small, but anyway, it is kind of readable.
Should. How about now? Should be.
Bit better. You have too many screens.
Well, hopefully that's visible to everyone in the audience then. So thank you again for the introduction. My name is Nathan Cook, and I'll be speaking today about an integrated platform for high performance data management and analysis at X-ray light sources. And before I begin, I want to acknowledge my collaborators, both at Radiosoft and at Brookhaven National Laboratory, where a lot of this work has been taking place. So as many of you know, light source user facilities are really productive technology drivers with a worldwide user base and a real diverse and growing range of applications. And this is really a big motivator for a whole lot of scientific activity in our community and technology creation in our community. A lot of our work right now is focused on supporting the NSLS2 at Brookhaven National Lab, which currently has something around 28 to 30 active beamlines, with many more planned, and serves upwards of 1,700 users annually. And this is an awful lot of users, an awful lot of experiments per beamline. And so a significant fraction of resources at these facilities is usually given to providing support for those users. And that support generally tends to come in two different flavors, both through beamline scientists directly engaging with users to provide commissioning and support of the beamlines and of specialized equipment and devices, as well as data scientists and computational scientists who are there to provide computing resources and software support for these users. And in general, this sort of workflow is really challenging. You really have to integrate multiple different constituents with varied expertises in order to make an experiment successful. So again, we have this sort of three different parties that are really trying to have to work together between the end user, who's the subject matter expert, the beamline scientist, who's the beamline expert, and the experimental procedures expert, and the computational scientist. And our work is really trying to integrate the interactions of all three of these through improving connectivity of individual software components. I'll begin by discussing the analysis component. The analysis pipelines in these experiments can be extremely diverse and specialized, and you can observe very significant variations in dynamic range, even across or within the same beamline. So I'm highlighting here 6 different analyses being performed at the coherent soft X-ray scattering beamline at the NSLS2. So this is really gives you an impression of the large dynamic range of experiments that take place on a single beamline. Oftentimes, in order to do these kinds of disparate calculations, you have to leverage a lot of custom libraries to provide the data processing and analysis support that's needed. And while many of these tools are developed by or supported at these facilities, so I highlight here different libraries, and you can kind of go to GitHub and see what NSLS2 software development is there to support different kinds of analyses. Even though these are closely related, they're not always directly linked to the control software. And that sort of does introduce some challenges for actually supporting all these different tools, and it requires a lot of effort by beamline scientists and computational scientists to support these user workflows. And so it's important that when thinking about these analysis pipelines in general, that we're not compromising custom workflows or sort of custom needs across these different application spaces. So what we're trying to sort of develop here is a beamline agnostic analysis platform and the workflow that supports this kind of analysis tools in a comprehensive manner. And the one that we sort of think is a promising solution and is currently in use at NSLS2 on some beamlines is that of Jupyter Notebooks. And so the idea of encapsulating the analysis within a sort of fixed platform but without actually limiting the sort of broad array of possible functionalities and tools. Jupyter Notebooks, as many of you are probably aware, is just provide a really nice environment for a variety of reasons. They enable these really nice rich text documentation. They have backends that are very flexible and can render a lot of different types of data sets and can do lots of different types of visualizations. And they can actually be deployed in a way that supports continuous integration. And this is a workflow that's used at NSLS2, where these notebooks can be, in principle, updated with the beamline on a weekly basis and deployed so that they can be incorporated into some kind of partially automated workflow using tools like Papermill to sort of launch these notebooks with reduced amount of guidance from the beamline scientists. And I'm showing here some examples of a workflow that's used at the CHX, or coherent hard X-ray scattering beamline at NSLS2, where XPCS analysis is automated through a sequence of Jupyter notebooks, which clean the data, apply masks, and then perform various different calculations. I think what I've described so far is a really varied landscape of analysis tools, but that's not necessarily always the case on the control side. And largely speaking, there's a whole host of very mature and sophisticated tools being used to carry out the experiments themselves. And the one I'd like to highlight here, and the one that we're working with, is the Blue Sky data collection framework, which is developed at Brookhaven National Laboratory and is currently in use across a whole host of facilities worldwide. Blue Sky is sort of a really cohesive set of interoperable libraries that allows for sort of a very well-defined experimental procedure through descriptions of different schemas, descriptions of hardware, and descriptions of how data will be produced during the experiment. And so it's a really promising scheme for carrying out beamline studies, and it's used pretty broadly these days. However, it still remains fairly decoupled from the kinds of analyses I described in the previous slides. It does have some tools for integrating callbacks or specialized data management solutions, but coordinating those tools is still very challenging, and it requires a lot of specialized input from the developers of Blue Sky. And so what we're trying to do here is sort of integrate the sort of disparities between the analysis pipelines and these experimental control pipelines. And sort of our proposed solution here, or what we think is a good starting point, is to treat the data analysis during an experiment kind of equivalently to how we would treat the data generation or the actual experimental execution. And to do that, we're leveraging our open source scientific computing platform, Cerepo, to basically act as the analysis orchestration, akin to the way that Blue Sky is being used as the experimental orchestration on these beamlines. So while Blue Sky may write to or may know how to talk to the experiment by basically writing out to EPICS and telling it to perform certain operations using the resources of the beamline, we would like to make Cerepo able to carry out different analyses by talking to different computational resources, be they local to the beamline or remote, say at a supercomputer, and execute those analyses and then return data as necessary, still in a format that sort of respects basically all of the different APIs and ecosystems that have been developed for data analysis with Blue Sky. So basically respecting the data broker library that's used in Blue Sky, and basically now enables the analysis to be done coherently with the experiment. And Cerepo, for those who don't know, it's an open source framework that we use for supporting simulations across a broad range of accelerator applications. And in particular, I'm highlighting here its applications to X-ray beamlines. Cerepo has been demonstrated to support simulations with synchrotron radiation workshop through an interactive UI, and I show on the right side here basically a panel from an interface that's demonstrating a simulation of coherent and partially coherent X-rays at the CHX beamline at NSLS2. And going further, recently, Cerepo has been shown to be coupled to Blue Sky, basically making use of Blue Sky's flyable asynchronous interface, which allows for non-blocking calls to launch simulations in concert with experiments. So we think that these sort of features if sort of brought to fruition in the experimental analysis workflow, will be really powerful for kind of adapting sort of an integrating a more improved and real-time analysis framework. In order to do that, the first thing we sort of have done here is to try and characterize the common analysis workflow that's being carried out at these facilities. And so what I've done here is kind of isolate what I think are the 5 sort of critical steps that have to happen in this analysis pipeline. The first of which is staging, and by that it just means down selection of data, querying from the available databases, and making available the types of data that are needed to process. Followed by pre-processing. This is very common where data will be cleaned. Basically, ROIs will be selected, masks relating to the devices might be constructed, and data reduction will be performed. Following that, analysis will be carried out. This is usually where the specialized tools come into play, and this is usually the biggest resource bottleneck in the process. And then documentation and post-processing steps will also be carried out. So here I'd like to show essentially what we're working with right now, sort of a prototype Serepo interface for performing this real-time analysis. And this interface is broken down into 3 essentially tabs in your browser to essentially carry out those different stages that I highlighted on the previous slide. The first tab is used for data selection. This is basically gives the user a capability to sort, search, and select from the available runs in a data broker catalog at that beamline, and basically make your initial down selection of here's the data that I'd like to sort of run through our processing pipeline. Once you've made that selection, you'll actually have access to more metadata and more different bits of information about that run within the metadata tab. And that basically uses these catalog schemas to populate even more metadata and provide more input on what analysis flags have been set to perform analysis on that data. And then following that, what you'll be able to do is actually launch sort of a predefined analysis, or that you've customized and loaded to the interface. And in this case, we're using Jupyter notebooks, which are deployed via pre-built Docker images to run this analysis. So essentially, once the analysis starts, that notebook will be launched. And as that notebook's being run, we'll see previews of figures being generated or any other reports being generated that you can click on within the interface. From a resource standpoint, this can be run locally, or it could be run on a site cluster or at a sort of a remote supercomputing system like NERSC. Right now, we're working on incorporating new mechanisms to improve real-time feedback of this interface. So that includes adaptive pre-processing for updating these kinds of masks and background subtraction and image region of interest selection that I described previously, as well as dynamic queuing. And right now, Serepo already supports asynchronous execution of multiple jobs per users, but we're hoping to enhance that kind of queue workflow to support more user configurability so that you can flag specific UIDs in Blue Sky's or data brokers metadata to be sort of high priority, and give those higher priority in the queue. You can maybe remove runs that don't look right, or maybe focus on runs that you're really excited about. And you can also prioritize the resources for those high priority runs as well by perhaps sending those to a more powerful machine for real-time analysis. And so that concludes my talk. Thank you very much for your attention, and I'll take any questions.
So thank you very much for being in time and having a really inspiring talk. May I, as a kind of a comment, ask you for your plans to, because it's the first time that a beamline gets a kind of a digital twin. How do you think to incorporate trained data via machine learning analysis to get speeding up of the real-time feedback?
That's a really good question. I think we've done this for guiding simulations before, and so I tend to think about processing the simulation results and the experimental results in the same way. So it's on the table. Blue Sky has allows you to sort of integrate callbacks that tend to be fairly fast. So you really don't want to be processing something that's going to take more than a second. So it's not clear to me yet how sophisticated your models need to be and how much customization the user might want in order to actually get that feedback happening in that time frame. So it's a good question. It's something I'd like to see explored, but I don't think we have plans to do that until we have a more robust system for handling kind of complicated machine learning workflows.
Thank you. I still would like to encourage you to pursue this. So I don't see questions. I don't see raised hands. So whenever you have something under your keyboard, you can fire your question into the question Q&A pipe or raise your hand at the moment. Otherwise, I would hand over to Dan. Dan, you're not heard. Dan, you're muted.
Yep, I was just giving a moment to see if any questions came up. Having none, I'll introduce Will Smith, who is a control system engineer at the Energy Materials In Situ Laboratory at BESI 2 in Berlin. He's been there for just over a year, having previously worked on controls and timing systems for a linear accelerator at Daresbury Laboratory in the UK and for the European Spallation Source in Sweden. He's part of a team at BESI 2 working on experiment control and data acquisition, also using a software package called Blue Sky.
Thanks for the introduction. Okay, I'm going to share my screen.
Take it away, Will.
Can you see this?
Yes, we can.
Yeah, great. Minimize this. Okay, I'm Will, and I'm going to talk to you today about the deployment of Blue Sky at BESI 2. I'll talk to you a bit about what BESI 2 is, the goals with the project, the benefits that we think there are to using Blue Sky, and the deployment so far at the facility, including how we've integrated devices, how we control experiments, collect data, how users are interfacing with the tool, and a short note on how we've looked at integrating machine learning. So BESI 2 is a synchrotron in Berlin in Germany that focuses on soft X-rays. It has about 50 beamlines and it's been in operation for over 20 years. So there's a lot of legacy hardware and software. To control the ring and the accelerator, we use EPICS, and we also use EPICS to control all of the beamlines. In the end stations, there's a huge variety of different control solutions. A lot of them are using spec, others use LabVIEW or homegrown solutions. So that scientists can do experiments, they need a tool that allows them to perform scans. And this needs to interface to pieces of hardware and set and read parameters, but also ingest other bits of information and then collect all of that together and do something with it. The tool that we use to do this, we want it to use a modern and widely used programming language. And I think this is really important because we want to be able to bring in people to the project who maybe aren't from this specific research community or don't have specialized knowledge. We'd like to use a tool that's open source and popular so that there's a community of other people around the world that we can rely on for help. And so that if any of the engineers and scientists we have working on it at our facility leave, we're not stuck. We want to make the data that's acquired at BESI 2 findable, accessible, interoperable, and reproducible, or FAIR. And we'd like to enable new areas of research in data science, produce intuitive tools to help increase scientific output, and write reliable version control software that could be centrally supported. So we looked at a number of options, but Blue Sky really fit the bill more than the others. It's based on Python 3, which is probably the most popular programming language in the world. It's open source and has an extremely responsive developer community. We've often found that problems we ask of other labs are helped solved within sort of 24 hours. So it's similar to the Tech Talk world in EPICS. It's in use at labs in the US, and there's a growing community at laboratories in Europe, which we now count ourselves as part of, and at other labs around the world. And importantly, it's got native support for EPICS with the OFID package. This diagram was shown in the previous talk, but I'm going to go through it again because I'm talking about some different stuff. So at the bottom on the left, we have the hardware that we want to interface to with our experiment, motors and detectors. And then above that is some software layer. Doesn't really matter what this is. Blue Sky doesn't make any assumptions about what it is, but for us, it's EPICS. And so here we expose individual signals controlling this hardware. The layer above that groups these signals from epochs into devices, and it's called OFID in the case where it's interfacing with epochs. And then these OFID devices are interacted with the Blue Sky run engine. And this is the thing that's actually performing the experiments, and it's kind of the center of it. When the run engine runs, it produces a series of documents which can be streamed over a network and ingested by other clients on the network. Those clients might do things like save to particular formats in persistent storage, or they might produce live visualizations. The other bit on this diagram, the data broker, is the bit that was mentioned in the previous talk. And yeah, it was just a fascinating talk. I'm going to go back and listen to it. So, the thing that's, when you're deploying Blue Sky at a facility, most of the work, at least initially, is in this bit, making sure that you've got a consistent control layer to your devices and in creating Python hardware abstractions to that layer. So this is what most of our time has been spent doing this year, and that's what I'm going to talk about now. My colleagues in the accelerator group created OFID devices for about 2/3 of the components of the accelerator, or the ring. And this is enough that they're able to do commissioning tasks and also to do other experiments in the accelerator. The ring is made up of many repeating segments, and it's a bit different in the beamlines. We have lots of variation between them, although they all use common components and interfaces. So I worked with colleagues of mine at the beamline that I work at, IMIL, to create OFID device classes for all of the components of our beamline. And the idea of making these sort of general classes means that we try and reduce the workload to deploy at other beamlines. We want to reuse them. So we're now in kind of production use at IMIL with this, and we're in the process of deploying at 4 other beamlines and have more planned in the future. Following the example set by other laboratories, particularly in the US, we have a collection of shared repositories. So we have one called BESI2 devices, which contains all of the OFID device classes that we use, and they're shared and just instantiated at different beamlines or installations. We have another repository called BESI2, which contains Blue Sky plans or scripts that can be used at different installations. And each installation has its own repository of tools. And by making this bit that's specific to each installation public, or at least public in our facility, it means that we can let other people see how different installations do it and hopefully share work and ideas. So now I'm going to talk a bit about some of the things we're doing with it. The first is continuous energy scans. We wrote a plan that was based on a flyer, but is a bit different. It's called FlyScan. And it instructs a monochromator to move between a start energy and an end energy at a particular velocity. And then the plan polls that monochromator and any detectors that is in its detector list, and it groups them together, saying that the readbacks from the detectors are at some particular energy. And this assumption holds, assuming that the monochromator is moving slow enough. So Blue Sky provided a powerful framework to realize this. One of the big benefits I think that Blue Sky has is the fact that OFID, this hardware abstraction layer, has native support for epochs error detector. And this immediately gives us access to a huge number of different cameras and detectors. We use this at my end station with the completely standard Blue Sky plan. We scan the positions of a motor attached to a fluorescent screen which the beam is hitting, and then by recording the image and the sigma or 4/5 half maximum of the beam spot in that image through area detector and then OFID, we can plot the size of the beam spot against the position of this, and we use this to perform an optimization of focus size. What I want to stress here is that we didn't really have to do much. We just connect all of these powerful packages together and get useful tools. So another really useful thing that Blue Sky has at its core is the collection of metadata. we looked at my beamline IMIL at how we could make the data that we produce findable, accessible, interoperable, and reproducible fair. So every time a Blue Sky run is performed, the run engine collects information about who the user is, what the investigation is, information about the sample and other metadata, and attaches that to information from the scan about what the devices are that we're collecting the data from are. And then this group of data and metadata is converted into a nexus format, which applies standard names to the different signals within it, so that somebody else looking at the data that we produce should be able to understand and reuse it. So the name given to monochromator energy in an X-ray absorption scan should be standardized. Additionally, we use a callback inside the run engine to write really important but boring information about what the scan is, what the sample is, who's doing it, etc., to an e-log. And this frees up time for the scientists to write about why they're doing the experiment. These two bits of data together, the e-log and the data in this standardized Nexus format, are then put into long-term storage. Our tool is called ICAT. And this is then findable, accessible, and searchable by people outside of the institution. If you'd like to read more about this case study, then I hope you can see this is WebLO 3, I think, also at this conference. There's 3 different ways that users are able to interact with Blue Sky. They can use IPython, which is probably the closest interface to spec. And this is really powerful. It has tab completion, and it allows you to get live visualizations. Other users we have really like using Jupyter Notebooks for all the reasons explained in the previous talk. And we find it particularly awesome for providing tutorials for people and showing them how to do things, maybe why they're working. Additionally, it can also produce live visualizations. The last thing we're looking at providing is a Qt-based graphical user interface. And we're using the Qt widgets that are provided as another Blue Sky package, also developed not by us. And here we really take this set of widgets and we modify them and customize them to be specific to what my users want. A graphical user interface is great because it needs less training than teaching somebody how to use the command line, and it makes, I think, browsing the data broker a lot easier. My colleagues in the accelerator group conducted a study in integrating machine learning methods with the Blue Sky Run engine. They connected a TensorFlow reinforcement learning agent to the Blue Sky Run engine using a Python package that they wrote called Naus. And the aim of the reinforcement learning agent was to reduce harmonic orbit perturbations. They found that this implementation was too slow for production use, and they're now closely following the developments of the Blue Sky Q server and Blue Sky adaptive packages and hope to build on that. And again, you can read about this at this conference in this paper. So next, we need to integrate more devices in the accelerator and a lot in the end stations and keep rolling out to other beamlines. And we shortly want to deploy the first working version of this GUI based on Blue Sky widgets and continue working on making the data that we produce fair. So to conclude, considerable progress has been made in the last year at BESI 2 deploying Blue Sky for the accelerator and for the beamlines, and we're joining a growing and active community of users and developers around the world. Blue Sky provides us with a set of powerful tools that we can customize for our users-specific needs, and it's critical to us realizing our fair data goals. I'd like to thank all of my colleagues at BESI 2, and of course the developers of the Blue Sky packages, and now I'd like to ask for any questions. Hello?
Will, you have a question from, oh, sorry, I've lost my question window. Renan Peraldes asks, in the fly scan example you showed, was the undulator sync with the monochromator? And what are the perspectives for faster fly scans?
Yeah, so in this example, the monochromator is sort of linked to the undulator. they both set off to just start at the same time, and then the monochromator changes itself by polling what the undulator is. This obviously is basically consistent enough given the rate that we're moving at, but if we wanted to go faster, then in our specific example, we'd need to use hardware triggering. And at the moment, I would just replace the thread that wakes up and polls this stuff with something that's connected to the hardware trigger. At my specific beamline, this probably isn't going to happen soon and isn't very important, but at other installations around the hall, it will be. I hope that answers the question.
Thank you, Will. I would also ask, is at what fraction of the beamlines at Bessie 2 have you deployed Blue Sky?
So far one, mine, but we're in the last week we've deployed another 4. Like now that we've done one, going to another one is actually quite easy, at least to provide access to the devices. Of course, there's a lot of work after that to kind of create specific plans that are useful for that beamline and modifying and testing it. But yeah, at the moment, not very many, but more coming online in the future.
Excellent. Thank you so much.
Thank you.
So then let me take over, though. The theme is already set. So our next speaker will be Henrik Enquist from Max 4. Henrik Enquist worked at Femtomax Beamline as a beamline scientist, and now he's a controls developer. And he will present us with is done with FlyScan at Max 4. So Henrik, the floor is yours.
Thank you. Let me share my screen. This one. So yes, can you all hear me?
All good.
Great. So I will describe our efforts to perform continuous scans with position-based hardware triggers at the Max 4. A little outline. First talk about why we want to do continuous scans, and then a little bit about parametric trajectory motions, why we need them. Then an overview of the whole system we have built, how we generate the triggers, the procedure of a full scan, and then we show some measurements we have performed. We have, of course, met some challenges, and then we have an outlook and present to other people who have contributed. So the advantages with continuous scans are quite well known. We start in a normal step scan, the detector does something, collects some data, and then we have to accelerate, move to a new position, deaccelerate, and then settle in the right position before we can get the next image. This takes quite some time. And in the continuous scan, we just do this once at the beginning and once at the end, and then the motor moves continuously for the whole duration of the scan. So there's very little wasted time between the points. We can't use normal pseudomotors for any coupled motion because they will move not at all according to a trajectory. They will just move at whatever speed they want. And when one motor reaches its position, the rest will continue moving. So the trajectory will be quite weird and not follow the path at all. It can be improved by matching the velocities of all the motors. It's still not perfect because it doesn't move at the right speed along the trajectory, and it still makes detours outside of where it should be. So that's why we use parametric trajectories. And we use the ICALEPCS motor control system, and which supports parametric trajectories where we upload a table of positions versus a position value in any unit we want. And you can ask it to move at a given number of units per second along this trajectory, and it will follow it very nicely. So then the system we have implemented this for is a plane grating monochromator. So it's a mirror and a grating that rotate independently. I show some typical graphs of the angles versus energy. And the synchronization between these two must be very precise in order to keep the beam stable and with stable intensity on the sample. So the synchronization between mirror and grating has to be, well, nearly perfect. And this is how we have set things up. We have the ICALEPS running a number of motors. We have one motor as the master, which and the encoder signal from this motor is connected both to the ICALEPS for closed loop and to a Panda box, which is the unit we use for generating the triggers. And the Panda box then triggers the detector or detectors, and we use Sadhana to control everything. And more specifically in our setup at the beamline, we have also the insertion device, which sits on actually a separate network on a separate ICALEPS. So we can't put this on the same trajectory as the monochromator, but we're lucky in a way that we have very strict requirements for the synchronization between grating and mono, but it's much more relaxed between the insertion device and the mono, since the bandwidth of the undulator is quite wide. And in the present scope, we're limiting this to short scans, which means we can actually move the insertion device. It's a single motor just running the gap. We can run the gap on a linear trajectory. We don't need any fancy trajectories for this. So we're just moving it on a linear trajectory. And we send all the encoder signals to the Panda box so we can record them at every trigger point to make sure that we know where they were at each point. And still, of course, using Sadhana. In case this turns out to be too sloppy, then we can add a trigger signal between the two ICALEPS so they synchronize their motions with each other. We will require a little bit more software work to set this up, but it's a possible upgrade. We hope we won't need to. Then for generating the triggers, we use the Panda box, and this is a complicated layout. If we can ignore large parts of this because it's used also in other modes where like time-based triggers and such, and there's a lot of logic to switch between the modes without affecting the users, so they don't have to do anything. So if we just look at the important stuff, we get the encoder value reading from the motor to the in-enc block, and that then continues to the sequencer block that has a list of positions where the triggers should happen. And then we bypass all the other stuff and go directly to the output. And if we look inside the sequencer block, we also have a PCAP block. This is precision capture, and that triggers when it's triggered by the sequencer block, it captures the positions of all encoder signals that are connected. I only show two here, but we also have the undulator connected on a third input. In the sequencer, we have a table with positions in encoder counts. And for each position, we have a trigger condition. So position smaller than or equal to position, or the other way around, depending on the direction of motion. And we have one repeat for each one, so they don't accidentally trigger several times if there is a little bit of noise on the encoder signal. If we do a full scan, we start by Sadhana configuring the ICALEPS and the Panda box and detectors so they are in the right mode. Then we calculate and upload the table of positions to the Panda box. Sadhana will then move the motors to their start positions. And once they arrive, we arm the detectors in the Panda box and start the trajectory motion. Then Sadhana steps to the right and just sits there listening to new data from the detectors. but it has no influence on the running scan. So the ice bucket will then move continuously across the whole scan range. And every time the master motor reaches a new position in the list, the Panda box will generate a trigger pulse. The detector will get some data and send it along to Sadhana, which collects it. And once all the points have been measured, then Sadhana got all the data points and just saves everything to file. And we're done and ready for a new scan. Yeah, and here are some just an example measurement we've done. This is done on the FlexBus beamline. So measured nitrogen, an absorption spectrum of nitrogen. One scan is a step scan, then just switched mode and did the same thing again in continuous mode. And the two spectra looks identical. But they're not identical in all possible ways, because if we look at the time they took, the step scan took 248 seconds. But the actual useful time is, we took 250 steps of 0.2 seconds. So the actual measurement time was 50 seconds. So only about 20% of the step scan was time spent for useful work. And then instead in the continuous scan, it took 57 seconds. So we only lost 7 seconds, which is about 12% of the whole scan time. So you can either do 4 more of these and still, or do the same, but with 4 times better statistics in the same time. So we met some challenges on the way. And one is that motors won't be standing still while measuring. So it puts higher demands on the mechanics of stuff. So for example, if motors cause vibrations while moving, this will disturb the beam. And also the mechanical position when moving becomes important, because we rely on closed loop to keep the mirror and the grating in the right place. But if the mechanics are bad, like if there's a lead screw that pushes something and it has an uneven pitch, then there will be errors that the closed loop needs to take care of. And the more work the closed loop has to do, the worse the results will be, of course. It can be minimized by carefully tuning the closed loop. So in this little insert here, I showed before we optimized the closed loop, we had quite clear oscillations where each oscillation corresponds to 1 turn of some component in the motor system. I'm not quite sure which one. By tuning the closed loop, we could get this much better. Couldn't remove it completely, but it's got much smaller. Then on the detector side, obviously the triggers may come at a much higher rate, so the detectors must be able to handle that. And also the analog bandwidth of the detector must be high enough to not smear any small detail in the collected data. So for example, the ALBA electrometer, you can select the analog bandwidth of the front end. If you forget that at 10 Hertz and run a scan a very fast scan where stuff changes quickly, the whole spectrum will be very much smeared and shifted to the side. So not very nice. Just to keep this in mind, that the bandwidth should be sufficient.
Henrik, do you have the time in? Okay.
Yeah, I'm almost done. So the outlook, we want to put also the insertion device on the trajectory. So we can do longer scans without the mono and the undulator drifting apart. And the rumor is spreading that we can do scans much faster. So basically all beamlines want this. So we will be extending this to all monochromators at all beamlines, essentially, and also to more types of equipment like sample, translation, or rotation stages. Finally, this of course has been a team effort by the KITS team, both software and hardware. The insertion device group has been in there, and several beamlines have helped, notably here in the FlexBus beamline, who were the ones that took the data. So that's it. Thank you. Questions?
Thank you, and congratulations. There's one question in the Q&A from Shu Zhang, who is co-developing the Panda box, and she asks, do you register devices data like control and data acquisition system information into the run engine? So she writes Blue Sky, but I think it is meant Sardana. I have the same question. How do you coordinate the detector data with the movement? So because the Panda box has the capability to coordinate mechatronics with the detector data.
We don't use it in that way. We simply use it now for generating the trigger signals on a TTL to the detector. Then we stream out the encoder positions at each trigger point, and then we simply use this trigger number to correlate what is what. So we get the right data for the right trigger and the right image.
So time is your correlation measure. So you just have a global time which is coordinating all the data.
Yeah, well, it's the trigger number, since the Panda box just Sardana doesn't really care at what time the data was taken. It only cares that it gets the right number of triggers and assumes that they come in order. And then the exact time when like 0.5 was recorded, we don't really care. Just that trigger 5 is the 5th image corresponding to the 5th position with the 5th set of encoder positions recorded. So it's by number. That's a trigger number.
Henrik, there's another question from Maxim Bandike. Do you deal with the fact that the energy at PGM depends on 2 encoders? Are you using the grating or the mirror feedback to generate the trigger signal by the Panda box?
Yes, we actually tried to put an AND block, so that both so only generate the triggers when both the grating and the mirror are in the right place. It made no difference because they follow each other so nicely that we didn't need to worry about this.
Well, there's another question: is the motor motion truly continuous? Because you said that there's only that you have a trajectory table. So Thomas Lohnert from ICES asks this.
Yes, it's continuous. What the IcePipe does, it interpolates. We upload a table of positions, and then the IcePipe interpolates in between. So it generates internally like a target position that moves along the trajectory. And then it regulates the speed of the motor to stay as close as it can to that one. You can select if you should use linear or spline interpolation or other stuff. But it continues.
If there's a last question, then you have to move on. Which type of motors? Steppers, brushless, beards, or the motor do have? For
this one, it's steppers. So, we mostly have steppers. For if we use, we have a servo motors in a few places, but we usually control them anyway from an IcePipe by a step and direction signal.
So thank you. We have to move on. I hand over to Dan.
Thank you, and I will stop sharing if I find the window. Yes.
Thank you, Henrik. Thank you, Roland. Next up, we have Christer Engblom, who works at the Synchrotron Soleil within the Electronics and Controls group, where he specializes in motion control and nano positioning systems.
Hello.
Hello, Christer. We
share my screen. Yeah, I'm trying to activate my video. I'm It says I cannot, but I'm going to share my screen either way. Let's see. You guys have a picture?
I see it, yes. Take it away.
All right, okay.
Thank you.
So I will be talking a bit about the hexapod control upgrade we've been doing at Synchronton Soleil the last few years. And we're going a bit into the method and some of the results in which we've had. As I am Christer Engblom, and I'm speaking on behalf of Louis Mlono, who has previously worked on the project, who finished his contract a few months ago at Soleil. And we both work for, or in Louis' case, he worked for the Electronic Control and Acquisition Group in Soleil, where we handle electronics and control and motion control. So I will be briefly explaining what is a Stewart platform for the uninitiated. Now, the Stewart platform is has a relatively simple mechanical configuration. It consists of a positional plate and a base plate. It has 6 linear actuators, and these are connected to the plates via 12 universal joints. Now, this isn't enough. The other half of the configuration is, in fact, a controller configuration. And by controlling this mechanical configuration using a multi-axis control, using a specific kinematic model, we can actually, in fact, achieve 6 degrees of freedom movement, of which 3 are linear and 3 are rotary, as seen in the picture here. So at Soleil, we have identified at least 12 systems that use Stewart platforms in 6 different beamlines. The most common use cases for these are to displace mirror systems, often with micron precision. And this is a picture of, for example, a mirror system on the Galaxy beamline, of which I'll be speaking a bit later. Now, there are other use cases that we have. For example, we have cases where we move samples, and other cases refractometers. But the most common case is to move mirror systems. So these systems, they most often have control systems that are proprietary and black box, and they control these systems using kinematic models that are also proprietary and black box. What this essentially means after a few years is that we run the risk of product discontinuity. Basically means after 10, 15 years, or maybe even more, that we can no longer find the controller, and we could no longer control our systems if we were to run out of them. And as such, we have quite limited maintenance and support on these systems, since we wouldn't be able to handle them since they are close to us. And if we one day would like to add a more complex system on top, or a more complex kinematic model on top, we couldn't do so because they are close to us. So what do we want to do at Soleil? Well, we would like, if possible, to use our own control systems that is standardized, in this case, the delta tau power brick. And we'd like to do so using kinematic models that we have in-house that we can, to some extent, handle. So then we arrive at something we call the Hexapod project. And the main objective of the Hexa project, if I have a nice little sentence for that, is to apply a Soleil standard controller. Now, this control has been chosen from the Revolution project. There's a link below if you want to see it, read up on it. And we want to apply this solution to a generic Stewart platform. And apply this to beamline applications using in-house kinematic models. Now, the word generic here is the important word here, because we don't want to apply this to specific beamlines and then have it unusable to other Stewart platforms. So for the Hexapod project, between 2017 and 2021, we had Louis Amelino, initially on a 3-year apprenticeship and then on a 1-year contract. Of which he had, for his main objective, was to apply a Soleil standard control solution to a Stewart platform application in a beamline. Now, this is easier said than done. In fact, it's the 4th and final step of the Hexapod project, of which the first step would have to be to validate the kinematics, primarily in simulations if possible. Once these have been validated, we have to find a way to implement them and into embedded programming into our controllers, the PowerBrick LVs in this case. Once the second step has been finished, find a test bench, in this case, something we find online with us, something we can move about without any risk to an equipment nearby, and therefore validate our entire control process and its kinematics. And once this third step has been validated, we would be ready for the fourth and final step, which would be to implement it and use it in a real beamline solution. So just a few words on the kinematics and control. I mean, to move our virtual axis, we have our 6 axes. We need to move our leg lengths. And how do we do that? We need to have a function that moves our leg lengths in function of a virtual axis. And in that case, we need our inverse kinematic subroutines. Now, these are, even though they're not simple, they're fairly direct, and they're trigonometric in nature. In fact, it's the complicated part is going from using our leg lengths and calculating where we are in our virtual axis space using forward kinematic subroutines. Now, these are calculated using a numerical approach, where we usually need to converge into the same solution. Now, this is more complicated and it takes more CPU runtime to calculate, but it is doable. And I will mention a bit about that later, actually. Now, to achieve the control, you need the kinematics, the inverse and forward, but additionally, you need to define your workspace. For example, you need to make sure that your workspace respects your mechanical limits and security. For example, leg lengths are limited. And for example, if we would like to move this Stuart platform in a rotary manner, we cannot move it in unlimited, we can move it several rotations, for example. We would have the legs collide with each other, for example. In addition to that, the workspace needs to have a lack of singularity points in the kinematics. This means basically in each and every single point in its workspace, the kinematics needs to provide a solution in its inverse kinematics and its forward kinematics. There needs to be a solution going both ways. Now, this is just a mapping of the workspace using the test bench that we calculated a few years ago. Now, just a few words on the test bench. We found something online that was made for students. It's not for precision, but it's to validate a control principle. It was more than good enough. This contains 6 low resolution stepper motors that also have encoders, but are also fairly low resolution. The mechanics were not very good, but good enough for us to have a rough idea if it works. As for the beamline application, we eventually identified a use case in the Galaxy's beamline. They have a mirror setup called M2B, and this is controlled by a Stuart platform. Now, the use case is fairly simple in nature. We just need to insert and extract the mirrors to and from the synchrotron beam. However, this needs to be done with a very high precision, a few microns. As for the hexapod, it's controlled by stepper motors, but it has fairly high resolution. If I remember correctly, it was 100 nanometers resolution. As for the workspace, we were working with ±2 degrees in the rotary stages and ±30 millimeters in some lateral movements, for example. So it wasn't a big workspace in respect to how big the hexapod is. So what did we achieve? Well, here's a video of our happy Louis, apprentice at the time, basically proving that the system works. The proof of concept was validated in 2019, where you can see he's moving a little plastic bottle with water using all the 6 degrees of freedom in synchronized motion, actually, using the kinematic model. Now, having validated the third step, we were ready to go ahead with our Galaxy's hexapod implementation. So in 2020, and as you all know, it was a very complicated year, COVID-wise. However, we did find the time to implement the new controller solution. And in fact, it was the control solution was in production since 2020. However, the coordinate system was centered below the mirror system. I don't know if you can see it down here. In fact, the mirror is up here, but the axis of rotation was down here. Functional, but a bit complicated to use. So in 2021, in 2020 also, it was controlled by Soleil standardized tangle devices. So it was fully usable by the users, and they could use devices that were completely standard. In 2021, kinematics were improved. For example, the coordinate system was now centered on the mirror system, so the axis rotation was exactly where it should be. And we started metrology measurements, particularly measuring the performance of the old control system versus the new one. Now, a few words on the metrology measurements. We used laser trackers and retroreflectors. So you can see that we had 3 of them. In this case, we measured hexapod positioning precision performance using the original controller solution versus the new one. And without going into too much detail, we measured lateral errors during linear moves and rotational errors during linear moves. And with the old control system, we had roughly less than 10 microns peak-to-peak errors and 20 microrads peak-to-peak. We measured afterwards with the new control system. And in fact, we're roughly within the same specs. So that means our kinematic model was, in fact, I'd say comparable to the old system. So what does this mean in conclusion? Well, in the respect to our 4 steps in our hexapod project, they were in fact validated. So our in-house solution has been proven using Soleil standardized controller and our kinematics. And in fact, the solution has been shown to be generic since we have used them on 2 different Stewart platforms, the test bench and the Soleil beamline application. And this therefore proves that the solution should be applicable to other Soleil applications of similar nature. And already this open controller access, since we have fully access to the controller, is already proving useful. We have done system developments and we have new ones underway. What does this mean for the future? Well, this basically means that kinematic improvements are underway using metrology data to improve the kinematic models. And we can now use these kinematics for other system implementations in Soleil. Thank you for your attention. And if we have time and if you have questions, I would like to take them. I would also like to thank the Galaxy's Beamline and the Soleil Metrology Group for their help in our project.
Thank you, Christer. Leandro Martins asks, what kind of numerical method did you use to obtain the kinematic?
So basically, we presume that the system was fairly, it would follow its reference points in the virtual axis. And if it wasn't too far away from where we presumed it would be, we would find a local minima and we try to converge on that point using iterational points using linear approximations. This works fairly well if the system model is good enough and does the calculations fast enough. If we wait too long, instead of converging on the solution, in fact, we will diverge and we wouldn't find a solution. So we need to make sure the CPU and the algorithm are streamlined enough, so to speak.
Thank you. Leon Chen asks, how do you measure errors?
How do we measure errors? We did, using the laser trackers, we could measure, we measure at 3 points at any moving in points. We could measure the linearity of the movement. So we moved as, for example, in X and Z, for example. And since the laser trackers, they could measure at many points, we would measure the linearity of the actual movements. And then we could measure the distance in which they moved. Now the laser trackers, they have a certain precision in which they can measure as well. And if I remember correctly, it was in the micron level at a certain distance. And as long as we respected that, we could actually measure the errors fairly well.
Just one more, thank you. Just one more question from Augusto Harita, who asks that you said the application is generic, the controller code is configurable. Is the controller code configurable, or is there a previous application for code generation for each hexapod?
It is generic in the way that all we need is we need the coordinates of all the 12 fixation points of the legs. As long as we have those, we need those measurements. As long as we have those, the Stewart platform control should be fairly good.
Excellent, thank you, Christer. Then I'll turn it over to Roland to introduce our last speaker.
Yeah, so take all your concentration. It's the last stretch, it's the last talk of this session. So it's Isaac Linde from the scientific software staff of Max 4. He will present us how machine learning can help the automation at an MX beamline. So Isaac, it's your floor.
Hi, thank you. Yes, so hello, my name is Isaac. I'm a researcher. Oh, you already did the introduction, so I don't need to read the ones I have in my notes. So yeah, I'm going to talk about automating crystal centering for macromolecular X-ray crystallography. So let's start with the problem we're trying to solve. In MX crystallography, we want to expose a sample crystal to an X-ray beam so that we can detect how the beam is diffracted in the crystal. The crystal is held by a loop, which is held by a goniometer, which can rotate and translate the sample in 3 dimensions. So the problem is, how should we position the motors of this goniometer such that this crystal actually gets hit by the beam? Well, we can do what we're doing now in Biomax, and that is to manually center it. A human can look in a user interface and click on the crystal. The crystal is always being filmed through a camera that's attached to the goniometer. You click on the crystal, do that 3 times to center in 3 dimensions, and then you collect your data. But that's quite time consuming, and a human needs to be there the whole time. It's a bit tedious. Can we do it in an automated way? Well, yes, there's X-ray centering with a mesh scan. And this is sort of a brute force solution where you expose a large area around the loop to the beam, and wherever you get the most diffraction, that's where the crystal is. That's where you do your data collection. But okay, so that's a pretty good solution, but and it's used quite a lot. But the problem with this is, well, it's quite resource intensive. You have to expose all of these and then process them a bit, all this whole area around the crystal. And also it does some radiation damage to the crystal every time you expose it to the beam. And so we would prefer to only need to hit the crystal once when we actually collect our data. So if we can do what we do in manual centering, but with an artificial neural network instead of a biological neural network, that would be good. And that's what MX Aimbot aims to do. So a very quick introduction. I won't talk too much about how neural networks work, but I'll just give this short introduction. A neural network in general is a very flexible machine learning model which can be trained to approximate the relationship between given sets of data. In this case, the relationship between pictures of the crystal and the central locations of those crystals in the image. The type of neural net used here is a convolutional neural network, or a CNN, which partly consists of several layers of convolutions whose kernel values are iteratively being fitted to some given training data. The usual example of what a convolutional neural net can do is to learn to recognize things in images, like, is this a cat or a dog? But in recent years, people have been able to do some absolutely mind-melting things with these neural networks, like generate photorealistic pictures of people that don't actually exist, or create images from just a text description. But here we only want to find the crystal, so I've collected a bunch of data for that. So we need data to images to train it on, and images to test it on. I gathered this from the Biomax beamline at Max 4 using a script that watched the goniometer camera and took an image when it detected that the sample had moved a significant amount, as long as the image wasn't too blurry or too dark. Then I went through that and pruned out the images that either were seemingly duplicates or just didn't look like it could be useful. At the end, I had 1,517 manually annotated images, 60% for training, 20% for validation, and 20% for testing. Now, that isn't actually that much data, but there are tricks that we can use to help the neural network learn. The way computers learn is in some ways similar to us humans. One way we can help our neural network grasp the concepts is to first give it something easier but similar to do. If you know how to ride a bike, you don't need to learn from zero how to ride a motorbike. And if you know how to find a crudely drawn pretend crystal like this, then you don't have to learn from zero how to find a real crystal. So I wrote a script to randomly generate a potentially infinite number of these to sort of prime the neural network before I feed it the real data. A bit about the neural network in particular, and some optimizations are made to improve training. Its input is a 128 by 128 grayscale version of the image we want to find the crystal in. Another way we can increase the size of our data set artificially is to flip all the images also, because if you know where the crystal is in a given image, then you know where it is in the flipped version of that image also. But then we can use that to get additional variation in our data set. We can also utilize this at prediction time by predicting both versions of this image and use the average as the result. This is called test time augmentation, and it really improved results when I started using it. Early stop, you know what, let's not talk about that for time reasons. Anyway, here are some results. These are the results from my currently best performing model. It's hard to get a good measure of what counts as a hit here, but the median distance between the annotated point and the point that the neural net predicted is about 3.3% of the image width. There are some images from the test. These are some images from the test set. So the model has never seen these crystals before. These green circles, I don't know if maybe they're too small to see, but these green circles are the annotations. That's where I have judged that the crystal is. And the blue circles are the predictions from the neural network. It does a bit better in the X dimension than the Y dimension. And I think that that's quite natural. The loop gives some hint to where it is in the X coordinate. Now, unfortunately, there will always be some outliers where the neural network gets scared by something it thinks looks weird and something it hasn't seen before. And then it might pick just a random point on the background. We're gonna have to assume that it will happen sometimes, but it would be good if we can at least detect it. We can't catch cases when it finds a point on the loop or something, but when it's a lot easier when it accidentally hits the background. I tried a few different methods of masking out the background in these images, including random walker segmentation and just good old-fashioned thresholding. But this one, this is the most reliable one I found so far, where I first detect the edges with a canny filter, and then I dilate and erode those edges to just fill in any gaps in between. Then I flood fill from the background to fill any of these holes we might get. And then we get a pretty good mask of where is the foreground, where is the background. If it hits the background, then we know it has failed and we can fall back to some other method. So what are the next steps for MX Aimbot? It's time to conduct a full end-to-end test of this, which will simulate how it will be used in production. So where a beamline scientist would use it as if they were collecting actual data in the beamline. And we'll see if, like, is this, are the centerings reliable enough to let it run fully automatically and unsupervised? And if not, then we can at least perhaps use it to assist the user or give some sort of suggestion, but where the user still has final say over any centering. Here is a video from a previous test. This is not the latest or best model that's predicting this, but now we're centering the crystal. Okay, now it takes an image from each of these angles, and it creates a centering point, and it's now centered in 3 dimensions.
Could you please think about finalizing quite rapidly?
Yes, because this is the last thing. Yeah, thanks for listening. Thanks to everyone at the Biomax Beamline for helping me with all these tests. And thanks to the authors of the paper called Deep Centering, which was a big inspiration from this project. If you're interested in MX Aimbot or have suggestions or are working on something related, I would love to hear from you. So shoot me an email. Thank you.
Yeah, thank you very much. For the interest of time, I would ask to contact Isaac via Hoover or other means for any further questions. There's no questions, so I'm asking not for this. So I thank you, and I thank all the speakers, and I would like to close this session because the other room has caught up with the time schedule. So thank you for your attendance. Thank you for the speakers, and we leave the room, which is the right one, to the left one, where already the summary of the workshop has begun. So please join me in moving to the other section, and thank you for the local organizing for closing this room.